All right, today we are starting our unit on momentum. We defined earlier the notion of inertia and how difficult it is to get something to move, and we quantify that by using mass in kilograms. But now we want to quantify motion. This was Newton's idea. How do we quantify how hard it is to get something to stop? So this notion of momentum is something very familiar to us. It's very difficult to stop something if it has a lot of momentum. So if you think of a Big Mac truck moving along, which is a giant thing but not necessarily moving too fast, or a speeding bullet, which is a very small mass but moving very, very fast. Both of them have a lot of momentum and are very difficult to slow down. So Newton came up with the notion of momentum defined as a product of mass and velocity. Notice mass is a scalar, velocity is a vector, which means that momentum is also a vector. Don't ask me why it's the letter P. I do not know. The SI units are kilogram meters per second, or you'll find out eventually that they are also Newton seconds. Newton seconds. Kinetic energy, 1/2 mv squared, could be expressed as 1/2 mv squared, which is mv squared over 2m. So p squared over 2m is another way of expressing kinetic energy, though we usually just use 1/2 mv squared. So a quick example, if you have a defensive back, a 160-pound guy, runs 4.640s, pretty fast. If he's going full speed, his momentum is going to be about 580 kilogram meters per second. Then if you take a 220-pound guy, a fullback, he runs pretty fast too, but not as fast as the D-back. Then his momentum is going to be about 780 kilogram meters per second. So if he gets ahead of steam and he runs into the defensive back, he's going to win. So football is all about momentum. That's why they have these gargantuan guys out there. All right. How do we change momentum? So we know that if we apply a force, we're going to get acceleration. We can actually rewrite and write that equation and say if we're using average force, that would be m delta v over delta t. And then we rearrange and move the delta t to get F delta t equals delta p. Okay, so F delta t is going to give you a change in momentum. And that is so well known, it gives its own name. It's called the impulse momentum equation, where F delta t, a force over a period of time, is considered an impulse, and then delta p is just the change in momentum. So if we look at it mathematically, we say that the summation of all of the F delta t's, okay, the net force times time, is going to give you a change in momentum of object in your system. Notice F delta t is going to be, if we graph F delta t, we could find the area under the curve of an F delta t graph to get the impulse. Now don't confuse that with the graph of F delta x, because F delta x we did last unit, and that gives us work. Force displacement area under the curve is work. And if the force is in the direction of displacement, it's considered positive work. And if it's in the opposite direction, it's considered negative work. So we get changes of energy as a result of forces over displacements. We get changes of momentum for forces over time. So you hit a wall with a pile of hay. Which one is your choice? Obviously, you're going to choose the pile of hay. But why? What about your intuition tells you should do that? Well, you understand momentum. If you have a very small delta t, you're going to get a very large F. If you have a very large delta t, you're going to get a small f, and we're all about smaller f's. Nobody likes huge impacts. Okay, so here's a practice problem. I'm going to have you fill out the Google form with the answers to these practice problems. This is practice number 1, and I had to fill in some things that got left off the slide, so there you go. I'm getting too far ahead of myself. So I want you to read the question. Okay, right there. Okay. Read the question and come up with your best response, and then I will go over it briefly. So you do want to pause the video, try to figure this out on your own, and then I will discuss it. Okay. So we have a block. It's moving to the right at 10 meters per second. We're going to apply a force in the opposite direction. So we know that the answer needs to be either B or D, because we're going to have motion in the negative direction. Now the question is, how do we get the change momentum? Well, we're going to need F delta t. In fact, we're going to need to graph it and get the area under the curve. Fortunately, we have really simple data. So we have a little triangle, 1/2 base times height. 4 times 4 is 16, divided by 2, and that's going to give you 8 Newton seconds. So the answer is B. Okay, next one. This is practice number 2. And so if you read through the questions, there's a check mark by A, but read the questions anyway, because that's not, well, anyway, read the questions, okay? Okay, so hopefully you realize that question A looks like a correct response, because if you're going over 2 seconds to get the change in momentum, you want to get the change in momentum is F delta T, and we could get F by looking at the graph and the area under the curve. We know the initial momentum, so we could find the final momentum. That makes sense. The second one also looks correct, because the area under the curve is going to give us that momentum. So both A and B are correct, which seems a little bit odd, but let's keep reading. No, because the data is too scattered to determine the average force that is exerted on the object. It's a little bit scattered, but you could do your best estimate and figure out what the general force is. It's around 3 newtons over 2 seconds, so it's going to be about a 6 newton second change. And then the last one says no, because the student needs to know the direction that the force is applied to the object, because the applied force will be in the same direction as the change in momentum of the object. Aha! That is the actual correct answer. You cannot find the change in momentum if you don't know in which direction the force is applied. Remember, force is a vector. So it's either going to increase its momentum or decrease its momentum, or have the momentum increase to the right or to the left, depending on which direction you push it. So the actual answer is D. Okay, question number 3. Force probe is used to push a box down a smooth surface as shown in the figure. Frictional forces are considered negligible. Okay, go ahead and figure this one out and find the correct answer. All right, so hopefully you realize that you need to get the areas under the curve. First area from 0 to 2 seconds looks like that. Next area looks like that. And the last area looks like that, which is obviously the biggest area. And so you're going to have the biggest impulse or the biggest change in that interval of time. So the answer is C. Okay, concept question. So this is different than practice questions. These are concept questions. A ball of mass m is initially moving to the left with speed v. After hitting a wall, it moves to the right at speed v. In other words, a ball goes in, it bounces off the wall, it comes off at the same speed it went in. Okay? The change in momentum is what? Okay? Jot it down. What do you think the change in momentum is? Okay, well, here's how you work this one out. I'm going to draw a little picture. I have my wall. I have a ball that is moving to the left at a speed v, and it bounces and comes back to at the same speed, but in the opposite direction. So the question is, what is the total change in momentum? Well, we remember that the change in momentum is mv minus final minus initial, and those should have, hang on, that should have little vector signs on at the top, so I'm going to put little vectors up here. So final minus initial, I'm going to define to the right as positive. So I'm going to get mv minus a negative mv equals 2mv, because the final velocity was to the right, which is positive, and the initial velocity was to the left, which was negative. And so the total velocity is going to be minus a negative or plus 2mv. And that should make sense if you think about how you have a ball, and you basically are bringing it to the wall and you're bringing it to a stop. So it has a change of mv. Then you take the same ball and you push it so it goes out at a speed of v for another change of mv. So basically a double change from mv and another mv for 2mv. Okay, example problem. This one is not in your Google form. A 2 kilogram ball is moving to the left at 20 meters per second, collides with a wall, and rebounds to the right. If the contact time is 0.1 seconds, the average force the wall exerts is 700 newtons. Find the final velocity of the ball. And I've given you the answer there, but let's see how you figure it out. Once again, I start with a sketch of the wall and a ball that's moving to help me keep straight what's going on, because these are vectors. The initial momentum is going to be 2.0 kilograms times 20 meters per second, or 40 kilogram meters per second to the left. I'll put a little to the left here. To the left. Okay. Our delta t is 0.10 seconds, and our force is 700 newtons. We know that impulse momentum says that F delta t is going to be delta p, and the F delta t is 70 newton seconds, because I multiply my F and my delta t. So now I want to find, I have one of the velocities, I need to find the other one. I'm going to define to the right as positive again. So I'm going to say F delta t equals 2 kilograms times V final minus initial. But I have to be really careful with my signs again because I'm adding a negative. And then I divide and solve to find the final velocity, which is, in fact, 15 meters per second. Okay, another concept question. A ball collides with a wall. For each case below, the initial and final speeds are the same. The mass is the same. The contact time is the same. The final velocity makes the same angle with the wall as the initial velocity. For which angle in degrees between the initial velocity and the wall would the force be greatest? In other words, what this is saying is, if you have a wall and you shoot a ball in and it bounces off at the same speed, which one is going to have a greater change in momentum? That one, or maybe this one, where it comes in a steeper angle? What does your intuition say? 90 degrees would be like this. It would be like, woo, coming straight in and going straight back out again. Which one's going to have the greatest change momentum? So intuitively, maybe you would come up with the fact that the answer is 90 degrees, or B. And let me show you why. Let's do it vectorially. So we have a wall with a vector. We know that the change in momentum is P final minus P initial. And we have initial vector coming in. Another way to do vectors, though, is to say P final plus a minus PI. So if I take this lower vector and I flip it around and add it to PF, I get this for a total of delta P. So that's a pretty good size change in momentum. Now, if I do the same thing with the blue, which is the steeper angle, I get, in fact, a larger change in momentum. So in other words, the steeper the angle, the greater the change in momentum is going to be given by the force. Now, in your homework problem, you're going to have a similar scenario where you have something glancing off a wall at a 60-degree angle, and they tell you the delta T and the initial and final velocity, and they say, what is the force? So what you have to recognize is how you have to break this down into components. Remember, we're talking about vectors. So we have F delta T is M delta V. If we take our incoming velocity, I'm going to call it V sub X and V sub Y, and then I'm going to have my outgoing velocity. I'm going to call it V sub X prime and V sub Y prime. And I do that because I'm lazy and I don't like writing initial, final all the time. Just prime after the collision. That's a little bit easier. But I do recognize that I can break them into components. And I know that like Vx, for example, is going to be, well, it's going to be V times the sine of theta, sine of 60. And Vy is times the cosine, etc. So I'm going to use a little bit of trig. But what I notice is that the momentum in the y direction doesn't change. It just keeps right on going. And the momentum in the x direction definitely does change. So that's what you're going to have to do when you want to solve this problem. You're going to have to calculate what the change in the velocity vector is in the x direction in order to solve for f. And as always, with momentum and vectors, be very careful with your signs. Good luck.